I don't know why I did this on a separate video, but whatever. Let's do a quick example of the kinetic theory. So here, this is saying that we have the surface of the sun. Surface of the sun has an average temperature of about 5,800 Kelvin, ridiculously high. On the surface of the sun, though, we have hydrogen atoms. Hydrogen atoms have a mass of 1.67 times 10 to the minus 27 kilograms. And what we want to know is, what is the Rms velocity? What is the escape velocity? So basically meaning that how much velocity does it take for these hydrogen to leave the surface of the sun? And then based on these two results, can we then have a large amount of hydrogen escape? Can we have any hydrogen escape? And then basically why? So let's look at the Rms velocity first. So now we know that the Rms velocity is equal to the square root of 3 times kb times t divided by the mass. So here this is already in the appropriate units, Kelvin and kilograms. kb we wrote down a couple videos ago, so if I plug in my numbers, what I find is this works out to be about 11,991 meters per second. So this is the Rms velocity of the hydrogen on the surface of the sun. What's the escape velocity? Well, we know the escape velocity for part B, based off what we did in the last exam, is equal to the square root of, so this was what, 2g times m, in this case sun, divided by the radius of the sun. So, in this case, what I know then is the escape velocity then is going to work out to be something like 1.96 times 10 to the 7th meters per second. So in part C then we can say, does a large number of hydrogen escape then to surface of the sun? We can then say no, right? Because here this is only, what, 1.2 times 10 to the 4th, where this is 1. Let's basically call it 2, so 2 times 10 to the 7th. So this is much smaller than this one is, which basically means that, what, no, most of the particles are not going to escape. Can any escape? Well, again, the overall answer to this is yes. And again, the reason for that is, again, if we think about that Maxwellian distribution, so again, if I think about the velocity versus the probability, so again, this thing is basically doing this. So again, the Rms is here, which means that the majority of all the particles are basically in this region. But again, outside of here, we can have a velocity which would correspond to, say, this velocity out in this range, which basically means that, yes, a small number of particles are going to have an average velocity which is greater than this particular escape velocity, which means that, yes, we are going to have some particles actually escape and come in all different directions. Some of those come to us as actually solar winds. There are bigger sources of solar winds, but basically this is solar winds which are given off from the sun, which come to us. But again, the point here is, even though the escape velocity is much, much bigger than that of the Rms velocity, again, because of this Maxwellian speed distribution, we still have some particles which are coming to us. Again, a very small number of them. But again, there's a lot of hydrogen at the surface of the sun. So even if it's a small fraction, that's still a large number of hydrogen which are being sent to us. And again, this is what we call solar winds. Those solar winds will interact with our Earth's magnetic field, and if they have a high enough velocity, they'll actually make their way partially in, which will screw up a lot of our electronics and things like that. So, but again, there's much better ways to get solar winds, and we'll talk more about that actually in 206 by the time we get there. But